Now, let me just remind you a few things we did yesterday. I tried to convince you that our aim is to estimate the probability that there exists a function in the class with the property that the empirical expectation there is small, but the actual expectation is large. So you want to show that this probability is small, because this corresponds to finding a function which is almost an empirical minimizer, but is a bad function on average. So that's what we're shooting for. And the first inequality, the first trivial inequality we use, the fact that this is bounded by the probability that the supreme probability of the actual expectation minus the empirical expectation. Another remark, of course, is when I say probability here, it means sampling with respect to a fixed probability measure, but because it's an unknown probability measure, you have to do it in the worst case scenario. In the case where you go over all probability measures. So in fact, you have a supreme of all probability measures here and here. Okay. The first step we did in the analysis of something like this was to show that, well, we didn't, we just told you following the talking that this is bounded by 4 times the probability of the supreme sine xi greater than x over 4. And what we did here was the idea of symmetrization. So we got rid of this thing at the price of introducing an independent, so something like the double sample trick that Paul Williamson talked about yesterday. And another difference here is that when I write probability here, the probability here and the probability here aren't the same. Okay? Here, the only source of randomness comes from the fact that the empirical measure to select is random, because what is written here is simply 1 over n sum of f at xi. But here you have 2 sources of randomness. One is this, and the other one is this, where the epsilon i's are independent, symmetric, -1, 1 value of the variables. So you have 2 different sources of randomness. So on one hand, we gain something, on the other hand, we seem to have lost something. Now, I started to talk about covering numbers and packing numbers, and I'm going to go into that in a minute. The idea is to try to take this class of functions, which may be infinite, and try in some sense to make it into a finite class of functions, in particular to reduce it to handling a single function. Treat this inequality with just one function, and then sort of reduce the general case to this one. So that's what I'm shooting for. But before I do that, I want to do something which is not too difficult, it's very related to this. And it's just something relatively easy in 2 dimensions. Okay? First of all, assume that we have a set in 2 dimensions. And you want to compute its measure. Okay? Now, another way of writing the measure of the set is to integrate the characteristic function of the set. Now, the characteristic function is simply a function which is 1 on the set and 0 outside the set. Okay, so that's really easy. But now I'm going to use the fact that we have a product space. Okay? So you have one coordinate here and one coordinate here. So a standard application of what's called Fubini's theorem tells you that you can do the following thing. You can take sections of the set. Okay? Compute the one-dimensional, in this case, length of this. This gives you a number, right? For every point here in this axis, you get a number which is this length. When you integrate those numbers, you get the volume on the measure of this set. This is just a straightforward application of Fubini's theorem. Formally, what you say is that you take for every set A, the probability A is the expectation of the characteristic function of A. Now, in our case, this is the set A. Okay? It depends on two families of independent random variables. So one is the epsilon i's, one is the xi's. And the idea is you fix one family and you see what happens with respect to the other. Okay? So in our case, A is a function. It depends on the xi's, the epsilon's, all of them, not just one. And I'm going to do the following. I'm going to fix the xi's, get a function of the epsilon's, treat that, and then integrate with respect to the xi's. So this is what in probability theory is called conditioning. Only in this case it's much easier because the random variables are independent. So it corresponds to sort of having different axes. So this is the same as the expectation of current A xi epsilon I once I know x1 to xn. Okay? And now this expectation, okay, so let's write it like this. Okay. You fix x1 to xn, look at it here. You fix x1 to xn, you get a function which only depends on the epsilon i's. You compute its expectation, right? And then you take the other expectation. Okay? But what's written here is simply the probability. This is the integration. You integrate over a characteristic function. It corresponds to integrate over this section. So this is exactly the expectation of the probability of the set A given that you know x1 to xn. Okay? So that's exactly the same as doing this, only in a slightly more abstract way. Now the meaning of this is that if you want to compute this thing, all you need to do is the following. All you need to do is the following. I'll forget the fourth for a second. It says that the probability of supreme and sum epsilon I f of xi greater or equal than n epsilon over 4 is the same as integrating with respect to these random variables the following function. The probability that supreme f of sum xi greater or equal than epsilon over 4 given x1 to xn. So now how should we look at this, right? We take each one of these and analyze them separately. We fix the values of x1 to xn. Okay? And now we have to deal with something which depends only on the epsilon I. That's the only source of randomness. The probability here is the probability with respect to the epsilon i's in that sense. Now, the reason for doing this, and that's in fact the reason for the entire process of symmetrization, that's why we vectors in Rn. And in some sense, I forgot the original probability measure according to which I was sampling. It doesn't come into the game anymore at this stage. I have to handle this, and then I integrate it. Okay? So I could have, at this point, in different circumstances, I would have shown you the connections between this and some nice ideas in boundary space geometry, but I don't think that's exactly what you're interested in. That's what I'm interested in, but that's not what you're interested in. So all I'm going to say is that there's something which is deep, hiding, right? It's not the end of the story. There's some fundamental idea I'm not going to get into because that will take me another 2 weeks. So I'm going to stop at this point. Just remember that there's something hiding. I'm just going to handle this. So, now the problem is, you forget the expectation, you look at this. You have the probability, and now the probability is just on the epsilon i's. But the supreme f some epsilon I, f of xi, greater than equal to n epsilon over 4, for fixed sample x1 to xi. This one, fix the sample. I throw away the source of randomness, and I'm looking only at this. And now comes the idea of the covering. Okay, what I want to show is the following. Writing this is writing the same as, let's make this a spectator more, just for the sake of writing this is equivalent to saying that there exists at least one function for which this holds. So a sample, a selection of signs is in this set if you can find at least one function in your class for which is in the corresponding set. Okay? Now, suppose I was able, in some sense, to approximate your class of functions on that sample by a finite set of functions. So, in what sense? That every function in your class would have an element which is really, really close in this finite set. Okay? That would mean that if some epsilon I xi is large, I'll make this precise, and the vector gxi, x1, gxn is close to fxn, then some epsilon I gxi is large. Okay? The idea is you know that this quantity is significantly large. You know that the distances here are small, then replacing f with g shouldn't change much. Okay? And that's the idea. The idea is to find a finite set of functions which approximates this class of functions on that sample in the appropriate sense. And that's where the covering comes into play. That's the idea of epsilon covering. Now, I need to choose the parameters in the right way. And I'm going to do that in a second. But that's where the idea of covering comes into play. define an epsilon cover of a metric space as a finite set of functions such that every element in your space is epsilon close to one of the elements of the cover. Okay? That's the idea of an epsilon cover. Now, I have to specify the space and I have to specify the metric. So in this case, I'll tell you which metric I want to look at. So take F. Let UN be the empirical measure supported on the sample set. This one, 2x. Okay? This is just a sophisticated way of saying I'm assigning a weight of 1 over n to each one of the points in the sample. Okay? So each one of these points have a weight of 1 over n. And the way I'm measuring distances now between two functions is simply integrating the difference. And I define d and g as the integral of the absolute value f minus g dvn, which is simply 1 over n sum fxi minus gxi. Okay? That's all I'm doing. In a few minutes, I will generalize this and look at the p distance. Simply having p here and 1 over p here. This is the LP distance, which corresponds to a p here. Okay? And I'm interested just in p equals 1 for the time being. Okay? Now, suppose that you have, so let H be an epsilon over 8 cover of F with respect to this distance. Let's call it L1 UN. L1 UN is simply this distance from P equals 1. Okay. What does it mean? It means that for every function in F, I have a function in H for which this thing is smaller than epsilon over 8. Okay? Now, I want to make precise the statement I said above. Okay? If I know that the supremum is greater than n epsilon over 4, then I know that 1 over n, that there exists a function for which 1 over n sum absolute value epsilon I fxi is greater than epsilon over 4. So I know that. Remember, when I say there exists a selection, it means that I fix those. There's an assignment of signs for which this is large. Now, I know that H is an epsilon over 8 cover of this, of F with respect to this distance. It means that for every H, for every F, I can find an H which is close to F in that sense. In particular, there will be some F for which this is, right? Some F which is close to this F. Okay? So, let me just write it this way. Now all I'm going to do is to add and subtract g at xi at every point. This is 1 over n sum I g at xi plus sum x of I g at xi. Okay. Nothing smarter, just added and subtracted g of xi. Now I'm going to use the triangle inequality. I'm going to use it twice. First of all, I'm going to say that the absolute value of these two numbers is smaller than the sum of the absolute values. And then I'm going to take this thing and say that the absolute value of this sum is smaller than what you do if you take the absolute value of this side. So this is equal to 1 over n sum epsilon I xi plus sum. Now, when I take the absolute value inside, the epsilon i's are either 1 or minus 1, but when I take the absolute value, it's just 1. What we get is f of xi minus g of xi. Okay? Now, I've selected g to be close to f in this sense. There exists a function in the cover for which this is close. Right? This is the way we measure distances. This is the L1 UN norm. Okay? So I know that this thing is smaller than epsilon over 8. Taking this to the other side, you get that sum 1 over 8 absolute value sum g of xi is 0 equal to epsilon over 8. Now what does it mean? Let's go back to this one. What are you looking at this? Okay? If you have a selection of signs for which this is true, and if H is an epsilon over 8 cover of F with respect to the L1U, then there will be some function in there will be some function in H for which this is true when you replace this with epsilon over 8. Okay? Because take a bad sample which does a selection of signs which does this, then there exists a function which satisfies this, then there exists some function in your cover which satisfies this. So this is smaller, and the probability is supreme of G and H. Sum epsilon G at xi greater or equal to n epsilon over 8, where H is an epsilon over 8 cover of F over 1 u. Okay? So this is what we have. We were able to reduce the infinite problem to a finite problem. And all we lost was factor 2. Okay? That's it. Now, I'm going to do something which is, in a sense, very bad. I'm going to lose a lot. Yes?
Is H finite? Is H finite?
Yes.
Yeah. So why?
Well, I haven't said anything. I'm assuming that you said it has an epsilon, finite epsilon cover.
Certainly bound to something.
It has to be more than what bounded, because It was fixed by a sample. Afterwards, I'm going to have to integrate with respect to all possible samples. So I need more being totally bounded to this particular probability measure. I need to be totally bounded to any empirical. Okay? And I should be able to go over all possible measures. I'm going to get into that. It's going to be a big thing. But for the time being, yes, I assume that it is finite. Okay. So what I'm going to do now is the following. Let's look at this. And I'm going to write this in a slightly different way. I'm going to write this as the probability that there exists some G and H at point A. For which this is. Okay? Now, for every H in this set, okay, you fix one, take any one you want, there is a set of bad selections of signs for which this is large. Okay? And what I'm going to do is I'm going to say that the probability that there exists an H for which this happens is less or equal than summing up the probabilities for every particular H. I'm actually doing the union bound. Okay? What I'm saying, let's assume that this is the space of selections of epsilon. For every H, there is a bad region. A bad region meaning that this holds. Okay? So this is a region for H1. This is the region for H2. This is the region for H3. And so on. Okay? What I'm saying now is instead, I'm going to say, you want to estimate this? Take the measure of this, plus the measure of this, plus the measure of the whole thing of this. Okay? Now the reason why this is horribly loose, and this is the reason for all that this approach is in fact bad, is that you count things many times. Right? For example, this region, you need to count it only once, but you count it in this diagram 3 times. Once because of H1, once because of H2, and once because of H3. Right? So I'm losing a lot here. And as you will see, that will be the source of the looseness that in the sample complexity model. So what I can say is that this is less or equal than the sum over 4H in H of the probability that some epsilon I HXI is greater or equal than epsilon H. So I did what I promised. I took an infinite class and reduced it to a finite class. What I lose is that I have to sum over a lot of functions. The number of functions is exactly the size of an epsilon over 8 cover of your class with respect to this folder. Okay? So that's the price I have to pay. Okay, so now I have to show you how to solve this problem for a single function. Okay? That's what I have to do. How to solve this for a single function. And this is where classical inequality, classical concentration inequality comes into the game, which is called Griffin's inequality. Griffin's inequality, make sure I have no mistakes with the constants. Griffin's inequality is an inequality on the following. You want to estimate the probability epsilon I pi is greater or equal to some x. Okay? Where epsilon I are again symmetric minus 1, 1 value under variables, and A is a vector in R. Okay? Looks familiar? Exactly what we have here. Epsilon I, this is a vector in R. So the probability here is bounded by twice E minus half x squared divided by the norm of A in L2. The norm of A in L2 is sum AI squared. So, now all I have to do is to take this and plug what I have here. Okay? So, here, in our case, x is an epsilon object. AI is hxi. So I can estimate this thing, right? Because I know that the functions are bounded by 1, so x squared is bounded by 1, so this is bounded by square root of n. So sum hi squared is bounded by square root of n. Okay? I just plug that in, apply this to this, and I get the following. I'm going to do you get that sum of h and h, probability of what's written over there, is less or equal than the cardinality of the h. We have twice from there, e to the power minus n epsilon squared over 128, whatever the mistake. I'm not going to care much about constants, and I'm notorious for making mistakes like that. If it's 128, I'm sorry. Yes?
Just a question about these epsilon i's. Why don't we keep rounding up the epsilon I? It seems like you could have just set them if you wanted to begin with, or you drag them.
No, because you don't know how to. The problem is that you wanted to get rid of the expectation with respect to f. Okay? The reason to do that, the way to do that is to introduce symmetrization. Once you introduce symmetrization, the epsilon i's come into the game, and the probability now depends on the epsilon i's, but you can't set it. The question is, what's the probability of in the product space composed of the epsilon i's and the xi's for something to happen? Of course, if you can find a different way of doing things, you maybe won't need them. Right? I haven't proved that they're essential. I'll show you that the sample complexity is completely determined by properties of something related to this. Right? This is in fact almost a type approach. Not this, but you'll see. Now the h, I know what the h is. It's the cardinality of an epsilon cover, the epsilon over 8 cover. So this is twice the covering numbers at scale epsilon over 8 of the class f with respect to the metric 1 un e to the minus n epsilon squared over 128. So what I did, remember, I fixed the sample, I treated every sample separately, and I got this. Okay? Now I have to integrate with respect to all possible samples, which corresponds to changing this measure. Okay? So the actual result you get is that the probability that the supremum of f and f of E mu f plus E mu summarization times the expectation with respect to the sample, okay? So let's write it like that, of n epsilon over 8 and 1 u n times e to the power minus squared. So this is a certain estimate. And I want just to look back at the proof and to see where we've lost something. What are the chances that we, I want to try to convince you that this is a horrible number. But I want to show you exactly what's the source of it being horrible. So the first step was conditioning, right? So, sorry, the first step was symmetrization. It doesn't seem that we've lost much there, because I haven't shown you that you can use the argument in a reverse direction and start from a symmetric case and go back to what you started without losing much. So you have, this is essentially flat. Up to, losing a factor of 2 or 4. So that's not too bad. Then a condition, which is an equality. It's not an inequality, it's an equality, it's a higher plus there. Now I've treated every set separately. And then I went to an epsilon cover. Again, going from the entire class to an epsilon cover doesn't seem to have caused much damage because I lost one factor of 2. But I had a problem. Then I used union. I counted things many times. Okay? And I got this as a penalty. Okay? And this thing I got from using Griffin's inequality. So people might ask, okay, maybe you can improve Griffin's inequality, get a better estimate, a better tail. Right here you see that the connection between n, the size of the sample, and epsilon, the accuracy parameter in the exponent is n is something like n epsilon squared. You might hope to get something which is n epsilon. You could do that under certain assumptions, but it's not that inconceivable. But that's not the worst thing, right? This is the problem. This is sort of helps you just a bit. This is the major issue. You counted things many times. That's one problem with this bound, and you need a new approach to resolve it. It's not something you can play around with this proof and get something better. That's all that this gives you. And the other thing, which is also a problem, is how to estimate this. What we have here is the current numbers of the class of functions at a certain scale that can be better with respect to a norm. Right? The norm is given by a random sample, and then you integrate over all samples. That seems very hard to compute. And that was the problem. Now, the first result in this direction was proved by Baklik and Chervonenkis in 1971, a slightly weaker result. They only dealt with functions which are Boolean, so they are 0-1 value, and in their treatment, they used a slightly different symmetrization trick, and the current numbers that they got were different couple of numbers. They were with respect to L1, they were with respect to L infinity. Now, L infinity, the distance between two vectors in L infinity is simply the worst distance when you go over the coordinates. Okay? The L1 distance is when you average the distance between the coordinates. The LP is the average with a certain power. So the L infinity, saying that two functions are close in L1 is much weaker than saying that they're close in L infinity, because, for example, if you have just one coordinate on which they're very far apart, once you average over everything, it sort of eats out this influence. So if you have an L infinity covering numbers, they're larger. It's harder to cover things with respect to L infinity than with respect to L1. In some sense, when you look at the different P's, as you increase speed, it's getting more difficult to cover things. Okay? So L1 is the best you can hope for. And they got something with an infinity. Okay. So the next question I'm going to address, and I'm going to do that after the break, is how to estimate this. What can you do to estimate something like this? Okay? So let's have a 5-minute break now. Just 5 minutes, please.
Push the one high. Yeah.